Okay, so now comes an important question. Careful, don't rush and don't be induced by what I wrote here. This Q, do I care about the charge? I'm going to answer that, and the answer is yes.
Why though, if it's a scalar?
Good. The thing is, we always have positive and negative charge. Ooh, the glasses. We always have positive and negative charge, so we have to make a distinction between them. So the positive is what you see in that plot that is better than mine. Huh? So the positive charge creates around it, this is more or less conventional. So the positive charge creates around it a positive potential which goes to zero if you move far, far away from it. Okay, so now if I have a negative charge, I'll say around the negative charge I create a negative potential that as I move far, far from it, it will become zero. Yes?
Why isn't it linear? Like, why isn't it a straight line? Why is it curved?
Because it's 1 over r. If you make a plot of 1 over r, so if you start with r1, then if you put, let me start with r10, r10, and then you move to r20, so it's 1 over 10, then 1 over 20. You can make the plot and you see this is the 1 over r is this kind of shape.
Can we say that the only time we don't care about the sign is with electric field lines?
With the electric field, and the force is when we are just using the equation for the magnitude. Then yes, we
So
never.
electric field and force don't care about it. If we're dealing with voltage, potential,
yeah.
any type of energy, any type of energy,
Yeah,
or energy
the energy
thing,
will
we
be
care.
here.
Okay, that makes it easier.
So could you repeat that whole thing with Odea just one more time? Make sure I got it.
But-
Can you repeat what Odea or Odea?
Okay, what Odea was trying to summarize, she's saying
Yeah.
the only case where I'm not going to care about the sign of the charge is when I have the equation for the force and when I have the equation for the electric field. Because in those equations, I only want to get the number, the magnitude. For the force and for the electric field, I have to study the drawing, those configurations, those angles to get the direction. While when I'm talking about potential is just a number. So I do care about the Q because I'll have a positive number when the charge is positive, and I'll have a negative number when the charge is negative. So that plus and minus is not saying more or less. It's just a way to distinguish between these two charges. A difference? What do you mean?
Like,
I can call the Q any Q that I want.
I sometimes write little q, and sometimes write big.
What we are trying to use is if I start with a single charge, then I'm calling it big Q. And why? When I bring the second one, I was calling it little q, like my test charge. The little one is just to probe what was already there. Okay, now this new quantity, too many names today, too many equations, but this new quantity is very easy to deal with. Simple. And we'll play a little bit with it. Let me just tell you about what is this thing shown here. This is just a story about units. Energy, we talk on international system, we use joules, right? We already said this over and over. The problem is that 1 joule is huge energy for these tiny little things that we are talking about now, these electrons, these protons. So when we are talking about these microscopic particles, we usually use another kind of unit that we call EV. So if you see EV in WebAssign or anywhere, don't get scared. It's just a unit for energy. And the conversion is here. So where is this conversion coming from? The definition of EV is the energy that one electron has when it's in between two plates where the potential difference is 1 volt. That's it. So 1 electron, remember 1 electron is 1.6 10 to minus 19 coulomb, multiplied by 1 volt gives me 1.6 10 to minus 19 joule.
What if the problem that we're doing is more than one volt?
I-
Change it or?
They can give you 2 volt, 2 EVs or 200 EVs. That's the unit only.
So then how do we deal with that?
Then if you want to, if they give it 2.6 EVs, you can just multiply this number by 2.6 and write it in joules if you prefer. This is just a way to convert from one unit to the other. Okay, so now we can solve the problems. And you'll see that they are very simple, as I said. So let's keep these important equations on the board. This is the one that we already said. We do care about U. The sign matters. This is just a scalar. And the other equation that is showing up there is the equation that we got for work. But let me be careful here. This is work done by electric force. And this we said it's minus Q, and the potential difference, the final potential minus the initial. Even before we continue, this is the work done by the electric force. What would change in this equation, if you remember this? What would change in this equation? Instead of work done by the electric force, this natural work that is done, if it's the work done by a person, an external force. Let me try to remind you. Think again about gravitational force. I'm holding this object here, I let it go. The work gets done by the gravitational force, and this work is positive. Well, this equation here would, this will be negative number with a negative will give us positive. Now suppose I have an external person, an external force to bring it up.
At the same time that it's going?
Yeah, I didn't ask this question well. Let me say it again. Work done by gravitational force, just read gravitational force. We said that the work was minus the change in potential energy. That's what we just used. But when we say that the work is done by external force, what changes in this equation? Well, this is going to be plus delta P. Remember that, because if I carry my object from low to high up, I'm gaining potential energy. Yes.
Well, so in the earlier chapters, maybe chapter 2, we had a situation where you fall off a cliff or you jump off a cliff and you have your own.
These two cases.
Or you're pushed down.
But these two cases is the gravitational force doing the work.
Yeah, but let's say, what if something's here, and in addition to the gravitational force, you also do your own external?
Then you can go with a bigger speed initially, but still the cause of your fall is the gravitational force. If there was no gravitational force, it wouldn't fall. But this what I'm saying is, when the gravitational force is the cause of the work, then we are going from high potential to low. Okay, and then I have to put this minus sign. But when the work is done by an external force, it's me. So I'm carrying it from low potential to high up, so it's gaining potential. So that's why I put plus. All this is just to tell you that in this equation, work done by the electric force, I have this minus sign. But if I put work done by external force, I have the same equation but with a plus. I talked too much for a simple. So I just wanted to keep all of these equations board, and now we can solve the problem. The first one. The first one is that 17.4. They want to know what is the potential, what is the electric potential at a certain point, and this point is 0.50 meters, for these two cases. First case, positive charge. What should I do? Which equation am I going to use and which numbers do we get? Oh, it's already 110, sorry. Okay, no. You should tell me, otherwise I'll keep talking to you. Okay, so I'll just tell you a joke. Well, it's not a joke, it's a serious thing. One day, there was this professor, but it's a long derivation on the board. And he couldn't finish, and then he got stuck there in the derivation. And then there was a student at the end of the class said, "Professor, the time." And he said, "Oh yes, the time." And he was changing the time equation. You realize. Okay, so I'm not there yet.
Yes.